Okay. So this is the reason that we don't need them. And there is a terminology here. This variable that you see it immediately coming after this, it's called a bound variable. It's bound to a quantifier. Yes. So this is also a bound variable. Okay. Now there is also, let me write about this, bounded set quantifiers. Bounded set quantifiers. So sometimes, you know, for example, the universe of this course is a set, but something is not working for all possible choices. So we want to limit our points of view to a very particular subset of the universe of this course. Then we will talk about bounded set of quantifiers. So let me write it for you. So let A, capital A, be a subset. We will talk about these things in math form, but you have an understanding what I mean by a subset intuitively. So it means that if this is the universe of this course, what is inside, for example, if I take one portion of that, that is a subset. Yes? So if I choose a subset, let A be a subset of the universe of this course, universe of this course. So what we write is this. So sometimes we are interested in saying that for all x, not in the entirety of the universe of this course, but if I am limited to this set, then I would say for all x belonging to this subset, we have this property p of x. Or we can also say there exists a x, we want to specify, we want to restrict it more. We want to say that there exists an x in this subset so that p of x is true. So usually if you write this or that, this is called bounded set quantifiers. It means that your quantifiers are bounded to a particular subset of the universe of this course. Okay, let us do another practice. Can you write this without, can you write this statement into in an equivalent way, but without using it bounded set quantifiers? So let us write this one here for you. So I want, this is the bounded form. The variable is bounded to be in this set. Can you write it without, just with this kind of symbols that you don't have any belong to after that? So how should I write this equivalently if I want to? This is very ubiquitous in mathematics. Most of the time you see this, but this means that if you want to do it rigorously, you can replace it with unbounded, non-bounded set quantifiers. So how can I write this?
For any number x.
For any number x? But then I am not allowed to put it belong to, so what can I write here?
X is not inside of A or...
No, this is not claiming that every x is inside A.
No, but...
So let me just read it again. How do you read this? This is read in this way. For all x inside A, you have this property p of x.
But if x is outside of A, then we don't care about it, so we just return true.
No, but logically it is not so. So this tells you that for all x in A, p of x is true. This doesn't tell you that if you are outside A, it is not true. It might be still true, yes? Do you understand these differences? So it's very important to understand these. So again, this is easier. Let me write this one. So how can I write this? This is easy. There exists x What should I write inside?
P of x and x inside of a.
Exactly. This was easy. Yes? So when you say there exists an x inside A so that P of x is true, it means that I could find an x. On the one hand, it is inside A. On the other hand, P of x is true. Do you understand? Do you agree that this is the same meaning? Okay, but something like this for the first one. So what does it mean? It means that whatever you choose inside A, you know that P of x is true, for example. So how can you translate it in another language?
Couldn't you write the same thing? No.
No. If that's the same thing, it means that these are equivalent as well. But of course, you see that they are not equivalent.
Not the same thing when you replace the first letter. But
just tell me what to write, I will write. Okay, let us write this. I would write for all x, if x belongs to A,
oh,
then yes, px. So this also can be written in this form. Yes, if I am telling you, this is the same claim. I want you to understand that. If this tells you that for any x that you choose from A, as soon as you see x is inside A, you can conclude that P of x is true. So if you want to translate it, it becomes exactly this. Yes? So, but we use these. They are very, very famous, so we will always use these things instead of this. But it is possible to write this purely in terms of unbounded set quantifiers. Okay? So that's also something that I wanted to talk about today. Another very important, very interesting thing is the negation of quantifiers. So this is, I have already used that. You have it in your brain because we are from a human species, yes. So it means that this is somehow in our brain, we understand what to write. But let me just try to illuminate it together here. So let me write the title, The Negation of Quantifiers. Okay, this is a very important topic. So negation of quantifiers. Okay, so what I mean that I have this. I have the negation. I want to talk about the negation of the universal quantifier. I want to see what to write in front of this. And I want to talk about the negation of existential quantifier. I want to see what to write in front of this. Okay, do you have any idea?
Can't you just move it in?
We want to discover. We want to discover what will happen. But this is not, I don't say rediscover, because this is already in our brain. We want to write it formally here. So let us talk it in English. For example, this tells you that, what does it mean? Let us be careful about writing this. This means that this is not the case that for every x, px. For every x, px is true, for example. Now let us work with this English sentence. This is not the case that for every x, p of x is a true statement. Let me write it. Okay, if you read this English sentence, what do you understand from it? Because I want to say, somehow some people think that, of course, they think that the negation of universal quantifier should be non-existential quantifier. But this is wrong. So if you are thinking somehow the negation of this is somehow equivalent to this quantifier, this is not correct. You can feel it. I don't know. There is no way that I can teach that to you. But this means that this is not the case that for every x, px is a true statement. It means that, just say it.
That for every x.
No, it means that, come on, it's easy.
Doesn't it mean that for every x, p is not?
No. I am saying that this is not the case. You say that every x will work. I say no, this is not the case. So it means you are saying that every x will work. I am saying no, this is not the case.
There exists.
Yeah, there exists. So you need to start with this sentence. This is not the case that for every x, px is true. It doesn't mean that px is never true. It means that there is something that px is not true. Is that understandable? So this means that, therefore, this means that there exists an x such that px is not true. Agree? And if I start with this sentence, this is not the case that for every x, px is a false statement, then you would say this means that there exists an x such that px is not false. Yes? So then can you tell me, what should I write instead of question mark? The first thing, the negation of the universal quantifier becomes existential quantifier. But this is not enough. Because you see, a true statement at the end turns not true. So what I am doing, I am negating this one as well. Okay, so it's very important to realize that the negation of a universal quantifier is an existential quantifier in which your predicate has been replaced by its negation. Yes? Is that understandable? Yes or no? Yes or no?
Yes.
Okay. So let us do the same thing for the second quantifier. So what is this one? This you can write two ways. Okay. So, but yes. What is your opinion about this? This tells you that this is not the case. This is not the case that there exists an x such that p of x, for example, such that p of x is true. Just let us concentrate on this. So this is the sentence. There exists an x such that p of x is true. When you write negation, it means that this is not the case, that there exists an x such that p of x is true. You can write it in two different English structures. Yes? Yes, Alex, do you want to say?
Yeah, for every x, not p. Or
Do you agree with him? This is one way. Because you say that this is not the case that there exists an x such that this happens. It means that, okay, there is no x with that property. Okay? So one way is that, let me not write it. So one way of doing that is to write for all x, not p. Yes? But here you can also write it in a slightly different way, but of course this is the formula, because so far I told you that we want to somehow avoid using non-existential quantifier. But can I use non-existential quantifier here as well? Yes or no? So how can I write it?
there does not exist.
There is no x such that p of x. Okay? So both of them in this case is correct, yes? You are saying that there is an x with property px. If this is not the case, it means that if I choose all possible values for x, property p of x is not satisfied. Or you can say there is no x with property p of x. But if you say it in that way, you have to use the non-existential quantifier, but we want to avoid that, so this is why you see this in the books. Okay? So this is, I wrote it here, but don't use it, okay? But that's the same meaning. Is that clear now? Let us test your understanding. What's the negation of here? Then you need to prove. Because this is the rigorous way, this is what our brain understands. But let me just now ask you, what would be the negation of this statement? I would say don't rely on calculation first. Try to think a little bit wisely. You don't need to do the calculation. You can give me the answer. But if I want to prove that answer is correct, I need to use this, these, and the definition of that bounded statement to prove that for you. So what is this one? What is your intuition about? Just read it as a very clear sentence for yourself and try to negate it in your brain. Yes? Yeah?
For every x, where x is in a...
For every x don't belong in A, you mean? Like this?
Yeah, but
In pair brackets like this?
the way you wrote it above.
Aha, here. Okay, okay. So you say for all x, x doesn't belong to A, like this?
Negation of the x.
Uh,
Then not
yes, that's completely correct. The way that you did it is calculational way. I wanted to come to this after this. Yes, that's correct. Because he's using his previous knowledge and what we learn here. So you see here, I can call this a q of x. Agree? And then I have for all x q of x, just I learned what to do. I learned to change this universal quantifier to existential and then negate that one inside. Yes? So what actually Emil is saying is completely correct. So he's saying that I had this, but remember, qx is this statement. And then I want to negate that. So according to what we learned here, this means there exists x negation of q of x.
Not.
Yes, not q of x. And then not q of x is one of the lessons we had actually practiced this is very important for the exam actually. So if p then q, what is the negation of this? Do you remember? It was the first one and negation of the second one. Yes? So what we are writing is exactly the same thing. So it becomes the first one.
But the y is crossed over.
So I think you made this one. So this should be x belongs to A.
yeah.
Yeah, this should be belongs to A. Yes, sorry. This belongs to A and negation of the second one. So that's the correct, sorry. Do you agree? Okay, but now let me simplify this form. Let us go back to the bounded case. How can I write it in the bounded form? Can I clean this? Okay, so how can I go back to the bounded form? Just compare this one. Something we are confused a little bit. I think. Sorry. So let me repeat this again here for you. Sorry, I was excited a little bit. So let me just do it
for every x, not.
That should be there exist. Yeah. So let me do it. So I want to let me calculate this. Be patiently doing this. We want to negate this expression. We want to negate this expression. This statement. Yes? For this one, I learned what to do. Instead of this one, I can write for all x. I am confused, yes? Yes, I am very confused because I started with solving this simple one. So Emil answered this one or that one. Okay, so let us do it in order. I want to negate this one. instead of this one in this big pair of brackets, instead of that, what I can write for all x, x belongs to A, then px. Do you agree? This is the statement that I can write instead of this, but I want to negate it. Yes? This. And then in your head, you can call this capital, for example, QX. Now you want to negate this universal quantifier with this predicate. What we discovered by this discussion is that this is equivalent to saying what? Just tell me. It becomes existential 1. Yes? And then negation of QX. So far, so good. Yes? But then, let me remind you of this lesson that if I want to negate a conditional, we had this before. Negation of a conditional is the first one itself, conjunction with the negation of the second. That was the rule, yes? So what I do here, this becomes equivalent to there exists an x. Instead of negation of q of x, I negate this statement according to this rule we previously studied. So it becomes x belongs to A and negation of p of x. Do you agree? Everything is okay now. Now my question is that because we started with the bounded set quantifier, this answer is completely correct, but can you put this back in the form of a bounded set quantifier? Because usually when you start with a bounded one, it is better the answer in the final form be in the bounded form, yes? Just can you tell me what should I write the last step? Just compare it with this one. Compare the last sentence with that sentence. There exists x, there exists x, x belongs to A, x belongs to A, and p of x, the only difference is that instead of p of x, we have negation of p of x. So if I want to collect it back into the form of a bounded one, can you tell me what should I write?
There exists an x in A and not p.
Not p.
That
Yes?
was very intuitive at the end.
Very intuitive. So this calculation takes us to the very intuitive idea, yes? So I say that every x in A makes p of x true. Negation of that, it means that there is at least one x in A which makes p of x false. And this calculation, a little bit tedious calculation, took us there. But this is needed here because we want to prove that. The only thing that we can rely on are those things that we discussed about. But this is the proof that this also works for the case of bounded set quantifiers. Is that clear? Okay, let us do the same exercise. So sorry, I messed it a little bit up, but let me just do this one. Let us do it together again, because I want to continue a little bit.
Mr. Baba,
Yes?
can you erase the most right formula because it might be confusing?
Yeah, that's very good. Thank you very much. So now let us do the second one. So number 1 is done. Number 2. My goal is to negate the second statement. There exists an x in A such that p of x. I want to negate this expression. The first thing, tell me what I need to do. What should I do first? Instead of this expression, I replace it with this expression. Okay, tell me what should I write. So this becomes negation. I would write there exists an x such that x is in A and furthermore p of x. Do you agree? Now again the same story. I can take this one to be my q of x. So you can imagine this in your head that this is q of x. Then you know how to answer this. The negation of existential quantifier is what? universal quantifier, and then I need to do what? Negate Q of x. Do you agree? But now what you need to do for me is to answer what happens here. How can I negate Q of x? Do you remember the De Morgan laws? I want to negate a conjunction.
Not the first.
Not the first one.
Not the second one.
No. Or not the second one. Yes. So this becomes for all x. Not Q of x means not the first one. This means this. Or not the second one. Agree?
Yeah.
Okay. Of course we are done here. But again, the same story. Because I started with a bounded set quantifier, it is better to put my answer, the final answer, in the form of a bounded set quantifier. Other than that, we are done here. I want to return it back into the form of a bounded set quantifier. So what should I do? You need to compare. What is the definition? I want to go back. So this is for all. It means that I need to compare this one with that one. So I don't know. Do you remember there was a fundamental theorem when we were talking about conditionals? Do you remember? Any conditional is equivalent to what?
Not
It's a
Q and P.
Pardon?
Not Q and P.
No.
Not P or Q. No.
It's called counterpositive, but before that. Before that, we proved the theorem using only the table of truth, okay? So this becomes not P or Q. That was a formula. That was an equivalent statement. Any conditional is equivalent to the negation of the first one, disjunction with the second one. Okay? And now compare this one with that one. So what you can write for all x. Instead of this, let me write it first for you and then ask you. Can I write this in this way? So let me see. The negation of the first one, or... No, let me write it in this way. Okay? Now ask you, do you agree with me that this is the correct statement? Let me do this in a scratch paper. X belongs to A, then not P of X. Okay? How can I write this using this theorem? How can I write this? This tells me that this is equivalent, but with negation of the first one, which means this, or the second one itself. Do you agree? I am just using that theorem to convince you that what I have written here is equivalent to what was in the previous step. Agree? Okay, but now this can be written as the form of a universal bounded set quantifier. Yes? So how can I write it? The names are very big, but this is very simple actually. So what can I write this? Look, compare this one with that one. There is only one difference between these two. P of x has been replaced with negation of P of x. So if I collect it back, it becomes for all x belonging to A, not P. Yes? So what does it mean? It means that you don't need to be worried about the new rules for the bounded quantifiers. They obey exactly the same rule. Yes? So it doesn't matter. So from now on, so let me write them for you here. We had negation of this quantifier, P of x. We had the negation of this quantifier, existential one, P of x. So tell me, what was this one? It was exist x, not P. This one was for all x, not P. Yes, this was the original one that we started with, but let me write the bounded one here. So it is still on the board. The negation of this bounded set quantifier follows exactly the same rule, yes? So this becomes equivalent to there exists an x in A such that not P of x. And then negation of this P of x is completely equivalent to, for all x in A, negation of P of x. So you don't need to be worried about memorizing two different things. They are exactly following the same rule. But for the second one, we had a nice practice and proof. Okay, so that we reminded ourselves about a lot of things, yes? So remember, these are very important facts for the exam. You need to remember them, okay? Yeah, so let me keep this one, because the last thing I wanted to talk about, unfortunately, I want to mix these quantifiers. So that is actually very confusing sometimes. For example, we want to talk about what will happen if I have a bunch of these quantifiers coming one after the other. We can talk about it here. The negations we can talk. What about what they really mean? I want to put one more session to it, okay? And that is good, because next session I will actually complete this, and there were 3 geometry problems were left. I hope that you have been working on them. So I will solve them for you, and then we will finalize. We'll be ready for the exam, okay? So what we can do here, if I ask you to negate this, so this is possible for you. Forget about, I will talk about this, what they actually mean, how do you read them, how do you understand them later. But let us just do a practice for this. I want to negate this. I have a predicate in 2 variables, and then you see that x is coming after this quantifier, so that's also a bound variable, that's also a bound variable, yes? So this quantifier, this predicate is bounded by these 2 variables. It's expressed in terms of those 2 bounded variables. So you want to negate that. So what you need to think in this way, this one, if I want to call it q, do you think that I should call it q of x or q of y if I want to give this a name?
Q of x.
Q of x, not q of y. Because y, so let us also talk about this. Here, y is bounded. There is also one more variable. That variable is called a free variable. So if you just look here, you know at least something about y, but you don't know anything about x. So that x is called a free variable. It's free to be chosen whatever you like. So that is a predicate, but in terms of x, okay? So then it means that I want, otherwise, if you write q, then it becomes meaningless. Another way of looking at that, yes? For all x, q, y. It doesn't make sense, yes? So that's also another way to see, to understand that. So this should be q of x. And then you want to apply this negation. What will happen? According to the rule that you know, this becomes existential quantifier, and then I have to negate that. Agree? So this one is equivalent to this one. Okay, and now tell me, what is the negation of this part itself? So it becomes, there exists an x, I copy and paste this part, then I concentrate on writing this negation. So what will happen?
Every y.
Every y, exactly.
Is not p of
Not
y.
this one, yes? So if I ask you what is the negation of this compound statement of a mixture of quantifiers, the first one becomes this, the second one becomes that, this one becomes this. Okay, let me just give you one practice for the next time. So, I don't know, we talked about the limit of a function, x goes to a, and I told you that the limit of function is a little bit complicated if you want to discuss about them rigorously. The reason is that the precise definition of this statement in mathematics is this. For all epsilon greater than 0, there exists a delta greater than 0, such that for all x, if x belongs to the domain of the function, and this happens like this, then absolute value of x, f of x minus L is less than epsilon. So that is the exact definition of when you say the limit of f of x is equal to L. This is the rigorous definition, and it took hundreds of years people come to this definition, that this is a good definition. But forget about the definition. If you want, we can talk a little bit about why this abstract thing means the same thing that you feel with limits, yes? But what I want to say, I want you to translate this for me. Okay, so there exists an epsilon, for all epsilon greater than 0, there exists a delta greater than 0. For all x, x belongs to the domain, and this, then this. Okay? So then I want you to translate this for me. So it is clearly the negation of this statement. So what I am asking you, try to write the negation of this statement in a completely correct way. Okay, so this is happening. So don't think, because you know every one of us understand exactly the logic, but we need to do it systematically, because if the statement becomes complicated, we might make mistakes. But if we follow the calculations, we find exactly the statement that we want to. So this is your exercise for the next session.
Mr. Baba.
Yes. Let me make sure, for all epsilon greater than 0, there exists a delta greater than 0. By the way, this makes sense, yes? If you want to be rigorous, what does it mean? It is a bounded set quantifier, because it is limiting the number of epsilon to positive numbers, yes?
Right.
And the universe of this course is the real number set. So for all epsilon greater than 0, there exists a delta greater than 0, such that for all x, if x belongs to d of f, the domain of the function, and x minus a between 0 and delta, then f of x minus L absolute value is less than epsilon. Okay, now we can end the lesson here. So next time I will talk the last very small part of what is left. That's also very interesting. And then we have a nice package of mathematical logic. This is very, very elementary one, but at least you have a very nice package of mathematical logic. Okay. Next time I will continue a little bit. That's the last lesson, and I try to solve those 3 problems. Try to think about those geometry problems that are also interesting. I don't know, for some reason, in high school education, we don't study Euclidean geometry that much, and when you go to university, even if you go to pure mathematics, they don't study it that much. They just jump to analytical geometry. So I would say that it's very, very good to know a little bit about Euclidean geometry. It's very, very nice tool in your hand to think about. I think it's more than much fun if you want to sit down and discover the patterns in Euclidean geometry.
What does it say in the end? The f of x minus...
Absolute value of f of x. Let me write it properly. Let me make sure that you understand everything here. So, for all epsilon greater than 0, there exists a delta greater than 0. For all x, x belongs to the domain of the function, and 0 is less than absolute value of x minus a, less than delta, not implied. If this, then absolute value of f of x minus L, a is this number that you see here, L is that number that you see here, is smaller than epsilon. Yes. Okay, so if you don't have any questions, we can stop here. See you in 40 minutes, 50 minutes.